I am Roland Zhang from Keysight Technology. Today it's my pleasure to spend some time to talk about 5G and the related advanced signal analysis. 5G probably is the most hottest topic currently in the wireless industry, and so in this seminar we're going to talk about why 5G and why 5G choose the wider band, what that impact is, why people have to go to millimeter wave. Can we just stay on the lower band, have a better coverage? And also there are some new technologies coming up because everybody want to roll the 5G much faster, so we introduced dynamic spectrum sharing. There are a variety of ways to do that. And also, what's the impact for overall wireless industry, especially you look at so many signal off the air, and what's the impact to the humans? And and we're also going to discuss how you qualify the network, as well as what solution Keysight Fieldfox can help. First of all, let's look at what are the wideband signal, why we care. When we see wideband signal, that means it's a relative term. And really what that means is the much wider bandwidth. And this is all coming from Shannon theorem. And you look at this three formula, I kind of put it there, is oversimplify. The first thing is you look at the channel capacity. This is regardless where your frequency is. You could be in the lower band FR1 or FR2. FR1 means frequency range 1. That typically means you're 6 gig or below, or the newer standard 7 gigahertz and below. Or you could be FR2, frequency range 2, that's millimeter wave. That's usually referred to somewhere between 24 gig to 50 gig. So it's pretty wide range. So why we need a wider band? This mathematical formula make very clear. You want to increase capacity, you need to have a wider bandwidth. Signal to noise ratio is very important as well, but that's only is limited. That's how much you can do. For example, you have a 20 dB signal to noise ratio. You certainly have a better capacity, but there's some physical limitation on that. And but the bandwidth is the quickest way to increase the capacity. Same thing for your speed. You look at speed, spectral efficiency is also related to your bandwidth. And another part is we always striving to have a better modulation efficiency, and that means at each symbol, how many bits can represent the better, the higher the better, right? And of course, the higher the better. Just from mathematical terms, that also make harder for hardware engineer to design, have a better receiver to differentiate those symbols. So you have the basically there's some limitation in terms of a modulation scheme. All in all, these slides tell you the wider bandwidth is the quickest way to achieve better throughput. This is just an example in the satellite industry, DVB, S2, or various coding scheme. This particular one is adaptive coding modulation. We call ACM. This is largely used by most of low Earth orbit satellite links. For example, SpaceX, Starlink, or Airbus, OneWeb, so on and so forth. There are many satellite system, and eventually those systems probably most likely will go to 5G using 5G modulation scheme. But for now, let's just talk about DVB itself. And you can see is depends on the signal to noise ratio channel condition. You can change either the bandwidth or you can change the modulation scheme, so you can adjust what kind of throughput you can provide. So that's kind of way to kind of, from previous slides, that's how you can see each system. Basically, there are 2 or 3 parameters you can play. Signals noise ratio, that means your transmit power. You need to overpower your noise. And modulation schemes, how many those symbols can put on the constellation. And most important is the bandwidth. So you really, engineers play all those 3 parameters to get a better efficiency, get a better throughput of the wireless communication network. This is another way to look at the cellular industry, which we all very familiar with because we live with it. So you can see the bandwidth is increased from generation to generation from 25 kilohertz. That was the analog amps or ETACs if you happen to live in Europe or some part of Asia. And then that's for the first generation. Then you go to second generation, so on. Now we are in the 5G. We can get at as much as 400 megahertz in the millimeter wave band, get a super fast speed. And so you can see every generation is the bandwidth is wider and wider and wider. And of course, they bring some other challenge. The system gets more complex. The radio gets super complex, and you have to use a lot of chips to handle that. Instead of in the first generation, you can probably to build your phone with a discrete component. And today, everything you have to be on the ASICs. Just now we talk about how the wider bandwidth is such a critical part of 5G communication, or actually 5G, any communication. You look at satellite communication system, it's also pretty wider band. You look at the Ka-band satellite, that can be few 200, 300 megahertz bandwidths. It's not any narrower than 5G. The goal is to provide a throughput you need. And suddenly you cannot put a 400 megahertz or 200 megahertz, even 100 megahertz on 1 gigahertz band, because those bands are, most of the channel is meg or 10 meg, and you're lucky you get 20 meg. So it's not going to that's not going to happen in the lower band. The only way you can have a continuous wider band spectrum deliver higher throughput is on the millimeter wave, on the microwave frequency. And when you move to microwave frequency, and it's not just simply you move to microwave frequency, you're going to lose tremendously on the coverage. And here's a few. We're not going to go through each formula, but you can see the pass loss, right? The pass loss is very much related to the frequency, and then the Fresnel zone, which is to describe how the signal being blocked, is also very much related to your frequency. Then the higher the frequency you go, the Fresnel zone is that get narrower, get smaller, is easy to be blocked. And of course, the other losses associated, like weather, rain pattern, building block, those all become problematic for millimeter wave link. That's why today FR2 is a super challenge for the RF designer. And there's a lot of techniques you can use to achieve the coverage. In general, you're probably looking at somewhere 100 meters to 200 meter coverage, and in real urban or suburban setup. And so that's why 5G in the millimeter wave you need to have a lot of base station. That's what I'll call network densification. All right, this is another example. Just now we look at the the pass loss. This is actually a real example. We put a transmitter to test basically what kind of millimeter wave coverage you can get. And in this particular case, you can I kind of highlighted a few data points. You can see some of the in the tree. If you can see the middle circle, in front of tree and behind the tree is almost like a 5 or 6 dB difference. That's a pretty big difference. And the maximum coverage you can, or signal you can possibly receive, like a MAC 120 dBm, is about 180 meters. And this particular one, we use the CW transmitter. We use Keysight Fieldfox, which can acting like a millimeter wave transmitter to do this type of test. So that's the whole idea of this, is to give you some concrete example how the millimeter wave 5G will be very much depend on your surroundings, how the environment setting, your window types, trees, so on and so forth. So when you design, we're not suggesting you cut off your trees or tear down your buildings just for the sake of deliver 5G. What I'm here is saying is when you're planning your network, you need to take those into consideration. So just now we'll look at the physical level of 5G, and then now we want to dive a little bit deeper to look at signaling level, look at the whole how 5G being constructed to help us to deliver better throughput. Of course, we all very familiar with 5G band, have different FR1 and FR2. This basically kind of illustrate what are the bands available for in the world. Depends on your country. In the United States, you basically anywhere there's a lot of 4 gig below or 6 gig below. There's a FCC new auction going on with somewhere in 3.5 to 3.8 gigahertz, which is called mid-band. I will see that's probably most important band for 5G because it has a little bit good coverage, not as good as 2 gig and below, but it also give you a very nice bandwidth. You have a couple hundred megahertz to use, so you can provide a better throughput. And the real revolutionary system has to be on the millimeter wave. That means from 24 to 50 gig. And there are some 60 gigahertz, 66 gigahertz band also can be used. That's usually is the ISM band, and even more challenging in those bands for higher loss. And in order to measure 5G, especially the 5G spectrum, and very important is, or 5G coverage, sorry. And very, very important, you need to understand what are the 5G control channel being constructed. One of the challenge for 5G control channel is 5G control channel is very different from 4G. 4G here, what I mean is LTE. LTE control channel always fixed. That means the size is always 1.08 megahertz and always in the center and a very very consistent. Or 5G is different because 5G subcarrier spacing are changing, so the bandwidths are changed. That's helpful to demodulate signal. And also, even more later on slides we're going to talk about is 5G control channel not always on, and its direction also changing because beamforming antenna. Those create some challenges. And how we handle that, what's our definition of coverage? That will be a very good question we need to ask ourselves. And then in the next couple of slides, we'll have a more discussion on those. In the previous slides, we talked about 5G have a flexible bandwidth for its control channel. And the 5G is very flexible. In addition to the control channel bandwidth can be changed, depends on the on the subcarrier spacing, which can be from 15 kilohertz all the way to 240, and the future will have 480. And also the control channel location here we call SSB is a sync basically sync signal block, and SSB. We're going to, from now on, I'm going to use SSB because that's where control channel is. And so these are interchangeable. So the SSB location can be different, can be flexible, can be at the edge of the cell, or be in the center of the cell, or somewhere else. And this this flexibility allows 5G signal to kind of more design in such a way to avoid certain interference, or you have a 4G and a 5G get together, or even in the same spectrum. Later on, I'm going to talk about and you can avoid those interfere between 4G and the 5G, because 4G cannot change control channel always in the center. In the 5G, you can change, so you can accommodate both at the same time. So that's really, really helpful. And another concept in 5G is the SSB location we use is something we call sync channel raster. And why that's important is you think about 4G. When 4G, you try to look at the system, you look at the channel, and the phone, if the phone have no idea where the signal is, the first thing you want to search sync channel, right? And you will go through each channel grade, channel raster, which is 10 kilohertz apart. That can be a lot of channels to go over. And 5G, because it's such a wider band, if you use the same thing, that might be a problematic. First camp on the 5G base station may take much longer. So we use the sync channel raster, which has much sparse location. So the phone doesn't have to search every single location. They just have a very fixed location, which is not that many. So help phone to speed up the synchronization process. One of the key technology used in 5G is called beamforming. Put this way, if there's no beamforming, 5G will not exist. And let's just quickly look at what the beamforming means. Beamforming means is I can, the base station can control to deliver the energy to particular location. Why that's important? And it's important is just now we talk about the 5G pass loss. In 5G, because millimeter wave, you're not going to transmit long. Think about balloon, right? If the balloon size is kind of fat, you're not going to, then the extension of the balloon is going to be shorter. If I have the same volume, if I'm going to squeeze the balloon, make the balloon much longer, but even same energy, but I can cover much longer distance. And also, I only deliver the energy to where it needs. I don't have to blast the signal everywhere. So that will save energy as well. So that's why it's very important for to deliver beamforming for 5G system. In 5G, most of 5G base stations, or actually all of 5G base stations, are phase array, using phase array antenna, and to achieve the beamforming or beam steering. And here, let's just talk about beam steering, which is really means kind of associated with the control channel. Later on, we're going to talk about more. And let's say I have a control channel. I need to steer the beam to certain places. Let's see, from minus 60 degree to plus 60 degree at for example, every 10 degree I send out the beam. So so the mobile will listen to those control channel. So how do I control the size of beam or the width of beam? Is by the element of phase array. The higher the elements, the narrower the beam is. So you can see over here, give you example. The number of elements to the narrower the elements, then your beam is getting narrower. And next one is how do I steer the beam? The way you steer beam, you basically give to program each element's phase relative to each other, and that will control the beam direction, and so you can deliver the signal to where you want to be. And later on, this is the technology we use in control channel we call beam index. And so you can every direction which are associated with particular time slot, and you will deliver the energy to mobile. So if the mobile happen to be in that direction, we'll pick up those beams. Mobile will pick up multiple beams, and will rank, let's say, 1 to 4. And then if the first top one is available, then you deliver energy to the mobile. Okay, let's look at how cell phone to access the mobile network. Just now we kind of touched upon the beam index. So when the cell phone first accesses the network, the base station starts sending we call beam index, which is carrier control channel. Those beams are wider, to help cell phone to basically catch those signals. And as long as the cell phone see, hey, I see that signal or that beam index, then the cell phone will send a response back through the random access channel, and that will decide what kind of coverage you have. And as long as cell phone decides, hey, I got this beam I like, and I'm going to communicate on that. And in the data channel and the other dedicated control channel, you don't have to carry on those traffic doesn't have to go on those wider beam. You can be much narrower, give you better signal to noise ratio and range. And so that's the whole process for cell phone to access the network. So you can see very important here is make sure the beam index to deliver or the beam control channel beam, which is we call SSB index, can deliver to the area you want to be. That's how you decide what's your coverage. And that's the reason when you measure your beam, measure your coverage, you measure the beam index power instead of just simple channel power. This is another way to illustrate, the beam index. You can see we have different color scheme representing different beam index. So you can see in different time slot with base station sending out different beam at a different direction, and mobile any location mobile can detect which beam they pick it up. Typically, it will pick up a couple beams, not just one, and the mobile will report the ranking back to the base station to decide which one it should log on or available for mobile. And just now we kind of touch a little bit on the coverage test. And the 5G coverage test depends on the network. It can be a little tricky. The reason why I'm seeing tricky is in the 4G area, we just simply take a Omni antenna, put on the CW channel, or just simply measure one of the control channel. And the bigger control channel is broadcasting everywhere. And for example, you use the panel antenna, let's say 120 degree or 60 degree, whatever the number is, and you can easily pick it up using the antenna in the FR1 for 4G, and for 5G, because especially in the millimeter wave, and you have your energy you look at can be multipass, can be direct pass, which is you intended for you, or have some reflected signal. And also the signal is the base station is the phase array antenna, so it depends on the beam you're picking up. And at this time, if you measure coverage, you have to be a little careful what type of antenna you're going to use. And especially if you're going to use Omni type of antenna, you have to be conscious about that, because you will pick up more energy than phase array antenna, because you aggregate signal from our direction. That means even your Omni antenna make those measurements on your, let's say, spectralizer or any receiver. You have to be conscious your cell phone may not see all those signals. So you either have to put some fudging factor there to take those into consideration, or you have to use either horn or phase array Ideally, you use phased array antenna, but fortunately, phased array antenna is not always available for all the bands. The next best one probably is a horn, and that's I would recommend to use. But in some situations, certainly you can use use Omni as well. You just need to understand how different antenna will have an impact of your measurement results. Keysight Fieldfox, we design a system. We can use any antenna. This particular case which we show you is a phased array antenna measurement. So we take a phased array antenna. This particular one is 27 to 30 gigahertz. That's really target for 28 gig spectrum. 28 gig millimeter wave probably is one of the most popular band for millimeter wave system around the world, and so you can see, you can measure the bore size scan. You can do polar scan. You can look at the azimuth versus elevation. Why that important? You look at the bore size scan. You can pick up where the main beam is. Let's see, you measure a base station energy, so okay, here's my main beam. Here's side lobes, and you can measure the beam waves using polar scan as well. And the most important is how the energy being distributed in a 3D format, right? And even though this is 2D, but think about the location. You add your location, it really is a 3D. And because the beam is much narrower, so at any given location, when you move your body move down a little bit, or your antenna move a physical location move a little bit, can causing significant signal strength change. That's why in some of the millimeter wave coverage, when you just simply turn around or you move your phone or hang a little bit, you will drop the call. That's the reason why we do this 2D scan. Heat map show you azimuth versus elevation. You can see the center is really where the energy concentrated. Yeah, this is just quickly show you how how you make those type of measurement. And you can see, if you see the picture, it's pretty easy. You have a phased array antenna, and you connect to the Fieldfox, and you can measure beam power, multipass evaluation. You can do standard spectralizer. You can fix the beam. You can say, hey, I want to point into this direction, or I can make a real-time spectralizer. Or you say, okay, I find the highest beam. Now let's look at the beam index from the base station. So you can do that as well. And so you can see it's fully automated. Just now we talk about in 5G coverage is a bit of a different from 4G. 4G, I just measure SSB. I measure the sync channel and the reference channel, cell side reference channel. That's my 4G coverage, because virtually my channel is continuous on all the time for all the directions. And the 5G is different. 5G have one more layer. Yes, 5G still have a sync channel, secondary things, primary sync for phone to look at to get the frequency location. And more important is, if you want really for the phone to use the 5G signal, you have to look at which beam index you need to measure. And there are many beam index. If you are in FR1, that could be 4 or 8. And if you FR2, can be as many as 64. So let's see, just easy calculation. Let's see, you have 120-degree cell side coverage. If you have 60 beams, so every 2 degrees you have one beam, right? So that's important to understand. Where's if people say, hey, what's your coverage? You need to for 5G, you need to understand this is not just sync channel coverage. It's also the beam index coverage. That's probably more important than anything else for 5G. So here you can, in this particular measurement, you will see on the top is a table view, bottom is the bar chart. The top tell you how many cell sites I'm looking at. Right now I look at 3 of them. And the bottom see each cell site, or actually bottom show you the top A beam index. Those can coming from different cell sites, or just from a single cell size. You can look at the PCI value, which is a physical cell ID. You can look at RSRQ, RSP, frequency error, time difference, and so on and so forth. Remember, most of the 5G network is TDD, not FDD. There's a few FDD network below 1 gigahertz. Vast majority of them will be TDD. And that's very important, the time offset between each base station. Otherwise, you will lose the sync and causing interference between uplink and downlink. Just now we look at the physical layer, look at beamforming, SSB index, and so on and so forth. And now we want to talk a little bit, just touch a little bit of different mode 5G operates. And 5G operates in standalone mode or non-standalone mode. Most of the network today is non-standalone mode. And the standalone mode means when you set up a call for any UE or cell phone, it's all start with 5G. The backhaul is also particular design for 5G. That's the ultimate goal of the 5G network. Right? You don't want to rely on 4G, and all the phone setup is on the 5G. But the problem is it's very expensive to set up those networks because you literally build everything from scratch. That's why we come up a new system as NSA. That's the dominant mode. NSA mode means non-standalone mode. That means when the cell phone will be anchored on the LTE, and LTE will use the existing LTE network to deliver control channel informations. And 5G just provide data channel. And the benefit is you can give customers seamless coverage. And for example, your RC reporting, RC messages, it's all between your phone and the 4G network. When you start request a higher throughput, higher speed, then move on to 5G. And the NSA mode is allow you operator to quickly deploy its 5G network and also more reliable. The network will be more reliable because you can move, if you don't have a 5G coverage, just move to 4G or back forward, or from 4G back to 5G when it's available. And the bigger, so that's the biggest advantage. The downside of the NSA is a lot of 5G design feature, especially the ultra low latency. That's just out of window because you still pretty much controlled by the 4G network. So if 4G network have some certain disadvantage, you're going to inherit that. You're not going to get quicker setup, very fast response, those type of things. You're not going to get that in NSA mode. And for NSA type of measurement, since 5G is not everywhere, so you will involve a lot of LTE and 5G. We call internet tests. So you want to measure both 4G and 5G network, and to see what kind of coverage gap 5G has, and do you have a missing neighbors or missing beam index or beam index pollution. So those type of things is important for internet tests. Just now we talk about NSA mode. Right now, let's move on to another technology currently very popular in 5G deployment, which is the DSS, dynamic spectrum sharing. So what is dynamic spectrum sharing? Dynamic spectrum sharing essentially is use a 5G to take advantage of 4G network, existing 4G network. And you can use the spectrum or use the time slot or combination. So you can quickly deploy the 5G network without really building new base stations. And it's a software change. And there are certain things you have to give because you took a resource from 4G, so the 4G is not going to have the same resource. And also you have to deal with some signal lengths, so you will see some efficiency drop or capacity impact. Yearly, you will see somewhere 15, 20, or maybe 20, maybe higher than 20% efficiency drop. But the benefit is you can get 5G coverage everywhere. So that's very important for DSS. Here's a quick overview of what exactly DSS works. And so you can just simply look at the diagram. And you can see this is basically have frequency time, kind of think about that's a resource block for LTE. So the LTE center, that's the LTE channel. In LTE, there's the frame called the mmBSFN. It's basically multi-broadcasting single frequency network. And that's in the 4G network, but hardly anybody use it. And so basically 5G took advantage of that. Okay, I should step back. It doesn't mean 4G network not using those resources. It's just very few people actually configure that into mmBSFN. And 5G network took advantage since the standard already have that, and the cell phone know how to deal with mmBSFN. So all I'm going to do is I'm going to tell the cell phone, see, this particular resource is mmBSFN, and you don't look at those. And it's not available for you. So you allow the LTE phone still operating on the 4G network, complete transparent with the 5G existence. And you put the 5G control channel in that particular resource, and then the data channel can be on the same mmBSFN or on some other channel if you can avoid do a rematching to avoid the 4G traffic. And so that will give you allow you to do to run both 4G and 5G at the same time. This is a very easy software upgrade, but it's very complex in terms of signaling, scheduler. That's why there's a lot of overhead that's going on. So you probably lose 10 to 20% capacity because of that. So how the network can tell the 5G phone where to look for those, and essentially is basically use the SIP message. Through the RC SIP message will tell you, okay, where's the mmBSFN is, where's your configuration, and where they're located. So that's how 5G phone get to know how to transmit or exchange information with the node B. And in order to measure DSS, that means you need to measure LTE and the 5G NR at the same time, just like this screen. Here one, we use the field fox scanner. And you can see on the top is a 5G control channel, 5G multiple cell size, and the beam index. And the bottom is LTE, standard LTE and channel scanning. So you can combine both at the same time. You can turn on the mmBSFN, and we'll calculate the correct power level for both 4G and 5G. There's no impact on the 5G. It's more when you measurement, surely you have to correct the measurement for the 4G. In 5G, one of the very powerful tool you got to use is a real-time spectralizer, and this is an example why RTSA is so important. So you can see I'm using RTSA put into spectrograms. You can see this is the same channel, and you can see the 5G signal. Sorry, on the LT side, LT you can see the LT signal, the control channel very clear spelled out. And on the 5G side, you can see there's a 5G control channel as well if you look at the spectrum. And in this particular case, the 5G signal is about 3.6 megahertz versus 1.8 1 megahertz for 4G. So they coexist, but they're not overlapping with each other. That's why how the DSS works. So just now we discussed, how the 5G signal, different implementation, DSS, NSA, so on and so forth, and which is great. We also talk about in the millimeter wave band, 5G going to build a lot more base stations than 4G. Inevitably, people are going to ask, is that okay to build 10 times more base station? What that do for humans? And can we handle that kind of energy? And in order to, short answer, as as an engineer for the wireless industry, I can tell you yes, 5G is pretty safe, actually safer than 4G. But that may not necessarily true for you try to convince non-wireless engineer background person. And in order to quantify the impact, we need to look at the EMF measurement, electromagnetic field measurement. Just now, we kind of quickly touch base. There are so many systems out there we call network densification. There are different cell size, different implementation. Certainly, make people kind of a little bit nervous. So how do we measure? What are the regulations out there? So you look at the RF spectrum. There are two types of spectrum from a physics perspective. One is called non-ionizing system. One is called ionizing. Non-ionizing means when you transmit energy over the air, you don't physically change the property of atom. So you don't manipulate the structure, the material, or molecules. Versus ionizing, like an X-ray, suddenly that will break down the molecule and causing harms or causing some danger. And all our wireless system is below 300 gigahertz. That's usually that range. You look at the orange, that range is usually fairly safe. It does because it does affect the molecule in such way. Well, the temperature may change. You are looking at the non-ionizing, ionizing area. For example, you're at home, your microwave, so you can warm up food, but it doesn't really break down molecule, but will raise the temperature. And that's true for the other RF spectrum as well. And how do we quantify those? Well, we use we call EMF measurement. Essentially, it's a field strength measurement. It's calibrated measurement, so we know what at any given area with a particular antenna, you will know what kind of energy is. And different organizations. There's many organizations in the world work with between ITU and the WHO, World Health Organization. They generate different limit line for regulator to follow. So if you follow those limit line, you pretty much very safe. They have a plenty margin, by the way, for those limit line, and just want to make sure people are safe. How do we measure? In order to measure the electrical field, magnetic field measurement, what you do is because the energy coming from different areas. So you cannot just use directional antenna or any antenna for that matter. You have to find an antenna which have its antenna pattern is even for every direction. That's what we call isotropical antenna. It's perfect, right? That's why we use this particular antenna called triaxial antenna. Essentially, it has 3 probes inside the antenna and being polarized on 3 different directions. And so you can measure, when you make a measurement, you actually make a measurement reading, actually it's the 3 of them from X, Y, Z, then you sum them together. It'll give you the average power of that location. And this is we call field strength measurement. If you later, this is almost like a coefficient. And if you use different antenna, you can simply take your antenna factor and with this measurement, you can combine, easily calculate, okay, I'm using this other different type of antenna, what kind of energy I'm going to receive. But over here, since we really target the human body, so we just using this isotropical antenna rating as the baseline to measure what kind of EMF impact of in the particular location. So just now we look at all the physical layer measurement, 5G, signaling, 5G control channel. Next, we want to talk about network qualification. What that means is now the network turned on, how that perform from user perspective. To measure from user experience tests or network layer type of tests, you need to inject signal lines, and we have Keysight has the full range of tests we call NeMo network test 2. And NeMo test 2 you can use for lab installation, optimization, troubleshooting. Essentially, it involves a software, multiple pieces of software. You control different device. You can even control Fieldfox. And the device basically have a phone base. Phone base, that means you test that particular chipset, and we'll pull in the data from the network, and essentially tell you what the network is telling the phone to do. And then you also have a scanner measurement is completely independent from network. And if something happened, your call drop, for example, you don't have a coverage, then the scanner measurement will tell you why that's happening. Then you can combine all those data together, doing post-processing, and to see what are the bigger, in the bigger coverage area where you're lacking, what are the problem. Maybe you find that the phone always drop in certain location, even though they have a pretty strong signal. Then that's indicate you either have interference or you don't have, physical resources available. So it's very important for we call network qualification tests. Is how you qualify your network, verify that the whole network is actually working. So it's typically is for the larger cluster of cell site to be tested. And also you can compare. You can compare between 4G and 5G, or you can compare different, let's see, different carriers, different operators. So see who has better coverage. So both indoor and outdoor. Yeah, this is one of the key tools in the NeMo family. I just use one as an example. There are many. We call NeMo Outdoor. NeMo Outdoor allow you to connect. It's basically a data collection software. You can connect to many devices, and you can collect data. Let's say you have a LTE, you have 5G, you have LD Fieldfox. You can connect Fieldfox as a scanner or other scanner as well. You can make those measurements. You can combine them together, put on the map, and you can load the cell site database so you know where your call dropped, what kind of throughput you have. You can even test different device services. For example, I'm doing web browsing, or I'm looking at Netflix video or YouTube video, you can see the performance. You even can test voice quality and video quality, etc. So I'll give you all the use case. You can see it's more test user experience, test the network protocol layer, and also combine them with the physical layer, so you help you to troubleshoot the larger network issues. One of the new feature in Nemo Outdoor is working with FieldFox. In the past, FieldFox always working independent from Nemo software, and right now you can actually take a FieldFox just acting like a scanner to connect with Nemo, combined with the phone measurement. If you find you have a problem in certain area, you need to troubleshooting interference, then you can just take a FieldFox, disconnect with the NEMO software, and use a standard spectralizer or real-time spectralizer to troubleshoot the issues. So you can see is in your vehicle, drive test vehicle, you can have tools give you multiple functionality. Just now we talked about the advanced signal. We talk about 5G. We talk about various tools to help address the challenges. The last couple slides, I'm just quickly touch upon what is a FieldFox, how FieldFox can help you. And I'm really pleased to announce FieldFox. Right now, we expanded the FieldFox capability. FieldFox is a multifunctional tool for RF engineer troubleshoot cell size, look at the cables, look at spectrum, look at the interference with RTSA. And in the past, FieldFox cover all the way to 50 gig, but a 50 gig FieldFox does not have a wider band. And I'm pleased to announce over here, so we just extended the FieldFox wideband capability all the way to 54 gigahertz, and both for combination analyzer as well as spectralizer. In addition to frequency, we also expand the bandwidth from 100 megahertz to 120, and so give you much wider bandwidths to tackle 5G or other advanced signals. In terms of a measure capability to measure millimeter wave, FieldFox family has multiple way. Right, one is the current one we just announced. Is we have 32, 44, all the way to 54 gigahertz, 120 megahertz bandwidth, and it's a single unit. And or you can use, if you say, hey, I'm not doing wideband demodulation, you can use the 5X or 6X A model, which also go to 50 gig, and doing standard spectralizer measurement on RTSA. And we also have a flexibility to work with the OML down converter, and that will allow you to virtually you can extend your frequency to 110 gigahertz, and have a different down converter. You can see on the that blue small blue box is sitting on FieldFox, give you the tremendous flexibility to measure various higher bandwidth signal for 5G or beyond 5G. Finally, just want to give you a quick summary of what functionality FieldFox has. And FieldFox really have three pillars. One is we call hardware measurement. Here we see device measurement. That's cables, filters, your horns, your anything you can touch, right? Or you want to measure noise figure, and that's that measurement we call device type of measurement. Another is we call signal analysis. That's your spectralizer, your real-time spectralizer, over-the-air measurement, IQ analyzer. You can record IQ data, export the data to like MATLAB or some other tools. And so it's more around signal analysis. The last also have a lot of utility. We FieldFox support GPS, internal DC power source, and we also support mapping and the different frequency extenders. This will allow, you can see all those functions have a lot of function. Those functions are all software bit flip, so you can add those functionality at any time you want. All right, in summary, wideband signal like 5G NR is a complex, and millimeter wave make it even more challenge to measure network coverage, optimized network. And then there's some technology in the 5G like beamforming, massive MIMO, DSS, NSA is make a 5G network more complex. And you will require different tools to tackle those challenges. And the FieldFox will be the ideal tool for your work. And if you are interested to take a look how FieldFox can help you to address those challenges, feel free to contact Keysight. We will arrange demos. Or you have some general question about 5G deployment, feel free to ask that question as well. Thank you.